Hi, I'm Jun Wang. I'm a master's student studying computer science at the University of Washington. And on behalf of my authors, Chuncheng Chen, Jiafei Duan, Professor Dieter Fox, and Professor Ranjit Krishna, I'm presenting my work, Eve, enabling anyone to train robots using augmented reality. So I'll start with some background and motivation for this work. So one trend we are seeing is that robots are becoming more affordable and capable to assist with daily lives. We have tabletop robots that you can program and purchase for a few $100s. Anthropomorphic hands from usually academic institutions that are specialized for grasping tasks. Mobile robots that can navigate around the environment and perform various tasks. And also humanoid robots that can walk and talk like humans. And this is all moving toward the future of household robots, where robots can assist with daily lives or even participate in family activities. However, data is essential, and personalized robot training is even more crucial. Although we have different data sets, such as Grab, that contains detailed contact information for various tasks involving grasping, IO-Bench, which consists of different data for traditional tabletop tasks, and also OpenX embodiment from various companies and academic institutions that contain 22 embodiments, 527 skills, and 60 data sets for different tasks, both mobile and tabletop manipulation. However, many tasks require domain knowledge. For example, if you want to fold a clothes or water a plant in a certain way, then you need to fine-tune the trained tasks based on the pre-trained model. However, currently, collecting demonstrations is extremely expensive. For example, one common method is kinetic teaching, where the user physically guides the robot to a sequence of configurations, or teleoperation, where you use a specialized controllers to remotely control the robot. However, these methods have limitations, such as requiring a physical robot, trained human annotators, specialized hardwares. Also, since these robots are often situated in the lab, they also suffer from limited object variety. I'll now present our system, Eve. Eve is an iOS app that enables everyday users to train robots using intuitive augmented reality visualizations without needing a real robot. So the Eve pipeline contains of 3 stages. In the first stage, the user uses our app, which contains a series of AR visualizations to collect data. Then they combine the data, such as RGB data, depth data, and so on, into a voxel representation and feed that to train for imitation learning. And then finally, with the trained policies, we can deploy it on the real robot. So to be more specific, for the data collection process, our app consists of 3 AR visualizations for visualizing the robot's movement, 7 features to improve the data collection efficacy. And all the visualizations and features are motivated by a formative study and tested in an evaluation study. And for the real-world deployment, Eve collects RGB data, depth data, and as well as waypoint coordinates. We use Perceiver Actor from UW to train a transformer-based language-guided behavior cloning policy, and we evaluated with 30 task rollouts for the toggle switch task. Building on prior research and personal experience, we developed the first Eve prototype featuring 3 new AR visualizations. First, we have AR kinesthetic teaching, where the AR robot tracks the user hand movements in real time. We also have path history, where the robot, where we display a virtual trajectory line between different waypoints, and also allowing users to revert to a previous waypoint so that they can modify their collected trajectory. And finally, we have Invisible Robot, where the user can temporarily turn off the appearance of the AR robot to see the environment better. We conducted a 2-part lab study involving 10 participants who had varying experience in robotics to understand the opportunities and challenges of trajectory collection. In both parts, participants used various collection interfaces to record a sequence of movements, including pushing, picking, and placing different cubes. So in the first part, participants tried 3 state-of-the-art demonstration collection interfaces, including kinesthetic teaching, teleoperation, and AR2D2. AR2D2 is a baseline interface that proves that you can use AR data to train robots. And Eve is built on top of this. We conducted the semi-structured interviews about their experience, focusing on what features they liked and disliked about each interface. Although this part is not directly relevant to the design of the AR visualizations, it gives participants a comprehensive experience with robot data collection. In part 2, users used the initial prototype of Eve consisting of 3 AR visualizations. And aside from the semi-structured interviews, we also brainstormed additional features for the AR-based collection interface. And finally, each user completed a survey for SUS scores and a form ranking motion intent communication, user enjoyment, and preference for the visualizations of AR2D2 and Eve. We found that the path history visualization achieved the highest score on all metrics and significantly outperformed other visualizations in user enjoyment and preference. Also, based on the user feedback, we distilled 6 challenges users faced with the current AR visualizations. These challenges mainly fall into 3 categories: ambiguous spatial positioning of the hand relative to the robot, where it is difficult to see how far away the hand is away from the camera; design limitation of the robot and its trajectory, where some visual elements interferes with the collection process; and knowledge and feedback gaps, where it is hard to verify the data collection efficacy. Motivated by the findings of the formative study, we implemented 7 additional features to improve Eve's accuracy, flexibility, and verifiability. We are only showcasing 3 of them here. So first, we have trajectory replay, where we replay the collected trajectory and changes in the gripper state by using a partially transparent robot. It makes it easier to determine whether the robot collided with a physical object during collection, and also without overloading the computational resource of the iPad. Also, we have dynamic camera view, where we allow users to move the device to inspect the 3D world. However, the data collection must be conducted from a single camera view to ensure spatial accuracy. We also have hand position projection, where we display a virtual cast shadow of the AR robot's end effector. The projected line matches the dimensions of the end effector to ensure accuracy. Now, with the final prototype, we can collect a variety of tasks. For example, if you want to train the robot to sort different food, then first you can pick various points and then decide the point to spawn the robot. And then you can modify and collect an accurate trajectory by modifying the trajectory and using various features. And finally, you can replay the trajectory to ensure accuracy. And for the evaluation study, we did a user study with 14 participants of varying experience in robotics to evaluate the effectiveness of Eve compared to other baseline interfaces. Participants used 4 interfaces to collect demonstrations for 3 lab tabletop tasks. And a collection was deemed successful if the participant completed the task without collisions within 3 minutes. And we recorded the success rates, remaining time, and SUS score, and as well as motion intent communication, user enjoyment, and overall preference. So for the first task, we have toggle switch task, where the user needs to control the robot to press the switch to turn on the light bulb. For the second task, we have participants control the robot to sort food into different baskets. And for the third task, the participants need to control the sponge to sweep the red beans to a targeted location. All these tasks were motivated by a paper from Professor Feifei group, which asked participants what tabletop tasks they want the robot to accomplish for them. And we found out that Eve achieved the highest task success rate. In fact, this is the only interface that achieved 100% success rate across all tasks. And it also performed comparably to kinesthetic teaching, where the user physically moves the object. In terms of task completion time, system usability, motion intent communication, and overall user preference. Other than the quantitative findings, we also have some interesting observations. For example, when the user is using kinesthetic teaching, despite the method's simplicity, some users needed to rotate the robot's body during data collection to avoid collisions. And most users failed to collect successful demonstrations due to the difficulty when using teleoperation. And while using AR2D2, users often misinterpreted the AR robot's 3D position. And for EVE, most users preferred using AR kinesthetic teaching to specify waypoints, as they found it easier to maintain the hand's angle and height. So now I will briefly mention the limitations and future work. So one limitation is that EVE currently does not support bimanual manipulations, since users must press buttons during the collection process. And collecting demonstrations with an iPad in front of the body is uncomfortable. Future research could explore the use of AR head-mounted displays, which enables bimanual manipulation, voice commands, and better depth cues. We also want to support multi-view data collection in the future. And one way to do that is to use SLAM techniques to track the iPad's LiDAR pose and create a 3D map of the workspace, enabling the demonstrator to collect trajectories relative to this map. So in summary, EVE is an iOS app that enables everyday users to train robots using intuitive augmented reality visualizations. And it also enables personalized robot training by exposing robots to diverse objects and environments tailored to specific needs. EVE is compatible with various robot platforms and motion planners, since the code base is modular. We hope EVE will catalyze future work in AR-based demonstration collection for robotics and expedite the incorporation of robots into daily life. Thank you.
Feel free to come up and you can use this microphone for questions. While folks line up, I was wondering if you can talk a little bit about, obviously you talked about teleoperation and physically manipulating the robot, but you could also learn from videos of people performing these actions. So do you think of this work as more of an intermediate step while we figure out how to learn from long-term video and figure out what movements are relevant for the task versus what movements are error correction? Or do you imagine there are other applications where this would be beneficial over learning from video?
Right, so I think one benefit of our approach is that it provides better 3D interpretation of the world by training using AR and using depth cameras, which training using 2D videos might struggle. And I think this is also very democratic. Like this method can be easily scaled up because everyone has iPad and they can just install the app and start training the robot. So yeah.
Thanks.
So hello, it's a nice presentation. I'm Sheo Liu from University of Pennsylvania, and I have a question about like the multi-view, like in the future work. Like I just kind of confused. It's like the trajectory data is already 3D. Like why in the future we still need like a multiple like view perspective to train a better like robotic system?
Oh, right. So for multi-view data collection, I was referring to, for the current system, you have to anchor the iPad to a stand and collect from a single point of view. The reason for that is we want the collected voxel representations to have the same representation and same view as the deployed policies.
Yeah.
So it's mainly for like hand-eye calibration and alignment. But in the future, if you want to move the iPad or wear like a head-mounted displays to move around and collect data, then you would have some sort of like depth mapping.
Thanks.